Hi everyone, it's a pleasure to be here to do a talk on causal inference, and I like to keep things quite basic, so I'm not going to be I don't assume any knowledge of stats at all. It's going to be very visual, so I'll be showing you some diagrams and that'll be like the key part of this talk. So the agenda for today is split into 4 parts, but the biggest part is about the causal diagram, that third bullet point. So this is a primer on causal inference. Essentially, what is causal inference? Why should we care about it? And how do we go about doing causal inference? And then the bit at the end is going to be like a wrap-up, just going through the types of biases that affect causal models. So that'll be touched upon in the causal diagram part, but it's just going to be like a high-level summary at the end of the different concepts in causal inference. So about me, I have my interest in causal inference came about with my studies in economics, and I took modules in econometrics, so using mathematics and stats to basically linear models to estimate causal effects of mainly, say, public policy questions, economic models. And then the last few years I've moved into data science. I feel there's quite a lot of overlap there because you have this knowledge of linear models and then you can pick up some machine learning. You do analysis, say, in Stata for econometrics, and then like picking up Python and that kind of data science workflow, you can augment that from there. And I've been applying causal inference methods at Triptease. So it's a travel tech startup in London. We sell our products direct to hotels. Our products sit on hotel websites, and the main thing we try to do is help them to compete with online travel agents like Booking.com, Expedia, by increasing the number of guests that book through the direct channel as opposed to, say, an agency. So our products are really about trying to improve conversion rate for hotels, improve the guest experience on hotel websites, and also help them to acquire new traffic, which is what we're doing with our latest product. And then I've done a little side project recently called Apple Pie. It's a side project I've been doing where I've made a package to do something a bit more than stats models library in Python. So model diagnostics, whether there's a goodness of fit in a linear model, and even like dummy encoders, that kind of thing, just to improve my workflow. So let's begin. Why do we care about causal inference? So the main thing for me is that causal questions are ubiquitous across many different fields of applied stats. And on the next slide, I'll go into an example from today, which no, that's later on, sorry. So types of fields are things like social sciences, so like economics, political science, epidemiology, public health, and then the main thing that I see day to day working in a startup is, well, people in C-suite, executives who want actionable insights. The kind of questions they might ask are more about, if I do this, what's the effect? Or they might be trying to validate an idea that they want you to do, and you can estimate it later on. It's quite a common thing. So these are 3 examples from those fields. So like one thing might be, how does passive smoking affect the mortality of non-smokers? Quite a big public policy issue in the last 10, 20 years, so smoking bans. What is the effect of minimum wage laws on employment? Another big thing in econometrics 20, 30 years ago. And then stuff you might see day to day in software. What are the causes of customer churn at a software company? And if you think about those questions, there's a slight problem here. So with causal inference, the main go-to people have is, well, the gold standard is a randomized controlled experiment. And of these 3 questions, is that something that we can do? Unfortunately not. So where do we go from here? And this is where we go on to this next part, the ladder of causation. This framework was developed by Judea Pearl, computer science background professor. He started doing this type of work in the 90s. I'll just touch upon it very briefly here, but if you want to read more about it in a lot more detail, then have a look at his book, The Book of Why. That came out a few years ago, and he did a book about 20 years ago as well on causality. So that was something that I picked up after I'd had this knowledge of econometrics. There were some questions that weren't quite fitting in the work I was doing with big data. So ladder of causation, we have, say, 3 different tiers of looking at questions that involve stats. So right on the bottom rung there, you have association. And in principle, that's, say, how does a variable x1 correlate with your target variable y? And yeah, that's really in the realms of correlation and very basic descriptive stats. And then right in the middle here, which is where we're going to be today, is the intervention part. So we have this x1, but what we want to answer the question of is, what happens to y when I do x1? So this is moving from the language of, say, what if I do this, as opposed to how are things associated. And yeah, the counterfactual part is like even high-level thinking, like what if I'd done this instead? That's, yeah, like, really know much about that, and there's going to be probably some more developments on that in the future. So in the news today, some of you might have noticed this article in a few papers. It was about premature births and the relationship between that and later developments in social life, like the chances of becoming a parent, that kind of thing. And this is a late addition to the slide today. When I was on the train, I thought, oh, they're talking about this association, but no one was saying this explains this. I thought, well, this is strange. So on the left-hand side, there's the paper right there, and right over there it says association. So already it's talking about a language of the bottom rung of the ladder of causation, association between a variable x and a target y. But in the press release, it gets a bit more interesting. These very smart authors will be talking about, we say correlation is not causation. That's something that's kind of been embedded in stats of the 20th century and not really moved that far from there. But in the press release, one of these authors said something like, people who are born prematurely, they have like difficulties in social interaction at a young age, and that makes it harder for them to do these social transitions like becoming a parent. And that phrase, make it harder, that is like a subconscious language of causation. It's something that they might not even be aware of. So we have to be quite careful when we're thinking about the questions we're trying to answer and how we frame things. So let's crack on with the causal diagram. And with this, we're going to be mapping out the different variables for something that I'm working on day to day at Triptych. So our products, there is, say, our messaging product, a few other ones, and we're trying to work out what are the direct effects of those things on conversion rate. Let's proceed. So we're having a night in the tower, but if you look at these 2 images, we'll see that this is what the hotel looks like, and then down here, this is what you might have seen a few days ago if you're booking a hotel room on Google. So just a raise of hands, how many of you are staying in this hotel tonight? There might be a few of you. Yeah, so about 20% of people, and then keep those hands up if you booked a hotel room online. It's very similar to before, so like majority of you staying here tonight would have booked online. And that's one of the main developments in travel tech of the last, 10, 20 years really. People moving away from, say, high street agents to online travel agents and hotel websites. So let's think about when you might have been booking that room. You might have just typed in Tower Hotel London on Google, and you might think, well, there's just so much stuff going on here. You've got all these adverts at the top from the hotel, Expedia, Booking.com, and then on the side there you've also got the same thing, Booking.com, Hotels.com, there's adverts on the side panel. But then if we just zoom in to something, we're on the hotel websites, and on here there are two different, just on that page, there are two different ways of getting to the hotel website. So the first one on the left, that's organic search. So if you click on there, it will take you through to the hotel website, the homepage. But this one on the right, Google has this panel here that has like a default search. And if you click on the hotels advert where it says official website, click on that and it will take you through later in the booking journey. It will take you through to something called the booking engine. And that takes you like one step closer to booking a room. And for us at Triptease, it's product development. We're just thinking a lot about our different products and different things in the market. So even say the pricing, for example, how does that affect people's likelihood to book? And how can we improve the guest journey on hotel websites? So strip it down to basics. This is like an illustrative hotel website funnel. And as you go down, and this is something that applies across a lot of e-commerce. Right at the top, you might have, say, 100 people visiting the hotel website. And as very typical in e-commerce, most of those people will bounce. And what that means is they'd have just clicked on the page and they'd have done nothing on the website at all. They'd have just, I don't know, gone to drink some tea, gone outside, been distracted by something. And then of those people that haven't bounced, there'll be people that have done the search. They've got, okay, I'm ready to book a room, let me find the price and all that kind of stuff. And so you might have 20 people out of 100 who do a search. But even then, there's quite a big drop-off in the number of people who make a hotel booking. And for that, it might just be 2. So the conversion rate of people who've done a search, 2 divided by 20, you have 10%. And suddenly you're having a lot of issues in machine learning with stuff like imbalanced data. And in causal questions too, you'll have a lot of null data. So there'll be people that have not done a search, or people that have bounced, and you have not really much information at all about them, and you can't really use that for modeling that much. So it's an interesting thing to model. So what are the different factors that could affect conversion rate on hotel websites? So there are things such as seasonality. People are more likely to book at a certain time of the day or a day of the week, even some periods of the year such as Black Friday in November. That's quite a big thing the last few years for hotels to shift some of their inventory. Things like traffic source. So as we saw earlier, you have organic search on Google on the left, and then on the right you have the displayed advertising. And one thing we notice is that people who click on ads are maybe more likely to convert. Then you have things like device, people more likely to convert on desktop than mobile. That's a very common thing in e-commerce. And even something especially for the hotel sector is pricing. So online travel agents, many years ago, they would often undercut hotels. So on Google Space there, you might see the hotel website is 10% more expensive. And as a consumer, you might think, well, this is the same item, but it's cheaper through the OTA, the online travel agent. And that's a big thing that affected hotels, and one of our products has helped to shift that power away from OTAs and empower hotels to achieve this thing called rate parity, where they can ensure that their prices are the same as online travel agents, and there's no difference in pricing that would entice them away from the hotel website. So in terms of products, let's consider two theories that people might be having in like a whiteboarding session in the office. So it could be, well, I think that personalized messages on hotel websites have a positive effect on conversion rate. And someone else might also say, well, searches from Google on just the google.com page have a higher likelihood of booking a hotel room. And that also leads us on to the issues of experimentation. We'll find that one of those we can experiment quite easily, the other one is not the case. And this is an example of what our messages look like on hotel websites. So a personalized message might be, if you've been looking for a room to stay somewhere in 5 days' time, you might be displayed a message like this: last minute break, this is a discount that we can offer you, that kind of thing, or complimentary items. So in terms of experimentation, can we assign, well, this concept of treatment? So if you're trying to vary a variable, if you're trying to go through different values of a variable, say like a binary one, yes or no, if I get someone to do this, if someone does this, can you randomize it? And can that be a nice experiment? With personalized messages at TripTease, yes, that is something that can be done, and we do that a lot with our hotels. So we have over 10,000 hotels as clients. We have the scale of data to do stuff like A/B testing, but the searches from Google point, that's something we can't randomize. And if we're interested in the causal effect, we'd need something like the causal diagram to help us estimate that direct effect. So this is, I guess, the halfway point, and it's quite a chunky slide to explain. So this is the first iteration of a causal diagram. So here we want to map out all the domain knowledge we have about a problem, about a space. So let's say we want to model the direct effect of on-site messaging on conversion rate or conversion behavior. So the one that's not labeled there, Y, if we treat that as a target variable, and that's someone that's converted or not, yes, no. And then the direct effect of messaging, which is the box M, is the white arrow between M and Y. And this is something we have reason to believe is a positive effect from data analysis we've done many times before. So with a causal diagram, you can map out all the different variables involving a problem and map out the direct relationships between these variables. So you might have done some exploratory data analysis. You might have, okay, I've got all these variables in my data set with millions of rows. What are the correlations between M and Y, G and Y? You might find that they go against what you think the causal effect would be, and that is because there is this interaction in this space between variables that can bias estimates of causal effects. So I'll just walk through quickly these paths one by one, the arrows. So like the first one, if we start at the top, someone that comes from Google, from the data we've seen before, we think they're more likely to convert. They're later in the booking journey. We have reason to believe that there is this positive arrow, this positive association between those two variables. Well, it's not an association, it's a direct effect. And then the other one from Google source, so we saw earlier that people that click through from Google go straight to the booking engine. That means that as soon as they've landed there, they have done a search. Whereas people that would have gone from another source channel, they might not have, well, they wouldn't have done a search necessarily because they might bounce. So with that, we think there's this positive effect on people coming from Google on search patterns. And then going from search to conversion. To convert on a hotel website, you need to have done a search. It's not really quite at the stage where you can get Google Assistant to do the booking for you, but we can think that would be quite a strong effect, and that will have implications for modelling the direct effect of M on Y. And then the other two, so people that have done a message and then going towards a search, people that see a message, that button in the middle that says book now, if you click on that, that will take them straight to the booking engine. And from what we see with decent click-through rates, people who've seen a message are more likely to make a search. And then the final one, for the products we're doing, the direct effect we really want to estimate, we believe that an on-site message will make someone more likely to convert. And this diagram space itself, there are like different ways you can name it. So one thing that it's called in the literature is Bayesian network. And as a structure as well, it's a directed acyclic graph, a DAG. So you don't have cases where between two variables you have arrows going in both directions. That can happen sometimes. It happens in econometrics with stuff like modeling price and quantity and demand and supply modeling. And that needs special linear models to do that kind of stuff. And then, yeah, so having this space in mind as an initial start, how do we go about estimating this direct effect, the white line, or the white arrow? We need to consider different ways of going from M to Y, as that can bias estimation. So for any given diagram, if you map everything out, the temptation might be, oh, in a linear model, I'll add all the variables I have in a data set into the model and just run it. More features will be useful for me, but that's not the case sometimes, because that depending on the interactions between variables, that can bias your estimates of that direct effect. So the one thing we want to look for is these things called backdoor paths. So these are ways to get from M to Y through these orange arrows. And in this case, I'll walk you through these. There are two different backdoor paths. And let's say we start with a model, a linear regression, modeling Y just with M as the very basic model. And then we need to think, with these different variables, how do we add other variables in to give us a valid estimate? And so with that, you might think, okay, I can control for G or S or another variable. So yeah, there are two backdoor paths in here. So the first one is you can go from M to S to Y, and then M to S to G to Y. Those are the two paths that we want to block. And can you go from S to G? Oh, sorry. M to S to G to Y. Yeah, so one thing that might seem a bit confusing is you don't have to worry at the moment about the arrows and the direction they go. It's, if you think of it as like a flow of a liquid or something like water, and it's like you can find your ways if you push hard enough, kind of thing. I don't know, that's like one metaphor I might give. So there are lots of things that, well, most paths are not blocked, they're open, and we need to control for a variable to block that path. The one case where a variable where you don't need to control for something on a backdoor path is if you have this variable being a collider. And I'll go on about this towards the end in more depth. But if you have inside a path, so if I just do through this one example, so M to S to Y, that's not a collider. We can block that path with S. So we can control for S. S is actually a confounding variable because it has a direct effect on Y, and it's related to M, what we care about, the effect of a message. So in this case, a collider would be the case where M goes to S, but Y goes to S. So that S to Y arrow goes in the opposite direction. So you have these three variables, and then right in the middle we have S, and the other two variables collide into it. And if that were the case, we wouldn't need to control for that variable. But as we'll see in this next path, S is now a collider. We have M to S, G, Y, and in here we now have S, two variables, M and G, directly going into it. That's now a collider, and we said before that if you control for a collider variable, that will introduce bias into the model, so it's not something that you want to do. And so accounting for this, the fact that we have to control for it from the previous path, we now have to find somewhere else in that path that will enable us to block it again. So here, the next part is G. G can block this path, so we can control for that in the model. This is quite tricky in a way. So when I first started off with econometrics, this variable S, it's something that could be called a bad control. It's something that is caused by what the on-site messaging, the thing that you're interested in, and it affects Y. And that's something that's hard to get my head around until I found the causal framework done by people like Judea Pearl. It's helped me to augment my approach to causal inference. So in that case, we can have everything in the model. We can model the direct effect of M on Y, controlling for S and G. And there are some statistical concepts behind that. I won't really go into that into much detail because it can go on for quite a while and get confusing. But you might have thought, well, there's a bit more to it. That was our first diagram. There must be something else going on. And you're right. And it's the fact that these messages, by being targeted, they have trigger behaviors. So we now introduce this other variable called T for triggers. And now we have two different arrows going in. So there's trigger behavior on the website. So if someone hasn't been active for the last, say, or the first 60 or for 60-second period, then we will choose to display a message as a way of trying to encourage them to convert, go to the booking engine. So with this, we're targeting people that are really less likely to convert. So between T and Y, there is this negative effect. And then the other case, going from someone who's done a trigger or has had the trigger, they all get the message. So there is that strong, direct, positive arrow going in there. And now adding that into the model, we have another path, and that's MTY. And with this, it's like a classic confounder case. It is a common cause of the variable you're interested in modeling, M, and the target, Y. So we need to control for this variable. It will help us to have more precise estimates of the direct effect. And one thing that can happen is you could have, in this case, it might be you do a correlation between M and Y, and it could be negative. And that could come about because of having this omitted variable bias. If you didn't include that in the model, you'd have your linear regression say there's a negative effect. But why could that be? It could be the average conversion rate on the website is 5%. Someone who has the trigger behavior, their conversion rate might be 3%. And then of the people that see that trigger and get a message, 4% of them could convert. So that's lower than the average on the website, but that's an uplift of, say, 30% on people that have received that trigger. So that now becomes a positive effect as opposed to a negative one. And yeah, so one way we can do this, and we do this at TripTease quite a lot, is A/B testing. So it's something you can do quite well if you have the scale of data. So yeah, you have stuff like minimum detectable effect, and there's a lot of literature on that. Unless you have a high scale of data, you're not in a position to do valid A/B tests. So for most people, doing modeling of causal diagram can help them to estimate the direct effect with reasonable validity if A/B testing isn't available to them. And before I've done stuff on whiteboards as a way of trying to get my idea around a space, how do these different variables affect each other? And there's tooling that can help you to do this. Once you have very complex models with dozens of variables, hundreds of variables, and this is something that you'd see a lot in product websites, likes of Uber, all those kinds of big startups. They will have so many things that they can feed into their model, but to do causal inference, they need an effective way to automate it, to make it quite reliable. And yeah, this is an example of a tool I found online called Daggerty. So you can you can add variables in a web browser and map out a different relationship. So as you'll see in here, say to estimate a direct effect, you have to control on G, S, and T. And that was what we had said before from going through these backdoor paths. And you can see diagnostics on these variables. So things like this is the causal path, or here's a biasing path. And then there are many Python packages now that enable you to do this kind of stuff. So causality, causal graphical models, do Y. And then as a quick refresher on this, if we wanted to estimate the effect of someone clicking through on a Google ad on conversion rate, you have the confounders before of M and S, but you do not need to control for T. T, towards the end here, is a collider. Oh no, sorry. S is a collider. We have to block that as before. But T here is... S is a collider. Oh, this was going on about S later on. Yes, we don't need to control for T here. It's blocked by S. Blocked by M, sorry. We've controlled for S and M on their other paths, but in this final path, the longest path, G, S, M, T, Y, we've controlled for S, so that was a collider before, and now we need to think in this path of the grayed out S, how do we then block this path, this final path? And we can block it with M. So these three paths really need to control for two variables, M and S. You can also add in T if you're interested in seeing the effect of that, but it's not something you need in this model. So in summary about causal diagrams, they're great because you can map out all your knowledge of a domain space and make your assumptions explicit, which is something very tricky to do sometimes in such large models. It's a toolkit for applying or identifying the minimum number of control variables you need. So in that last one, you don't need to control for the triggers of messages. And you can iterate your diagrams quite a lot. And that's always nice to have if you have stakeholders who say, oh, like this is something else that you consider in the model. And then the final section here is just an overview of the types of biases that we'd seen before. So if we look at it as X, Y, and Z on which is just three variables, we're mapping it out, we've got our pens, and we can map out these things for this variable Z, and then we've got X and Y. We can add some arrows in and see, well, for this first case, you have the confounding variable, and through all these diagrams, we're going to have the direct effect of X on Y in purple, and then you have at the bottom the backdoor path. And for here, the confounding variable is when Z is a common cause of X and Y. And for that, you need to control for these types of variables. So in the corner there, you might see you have X, Z, and Y, and you've got the arrows going out from Z. And with these ones, you want to control for confounders. They will help your model's estimates. They'll increase the precision of estimates. They'll help to reduce the bias. And then colliding variables, you have it the other way around. You have Z being a common effect of X and Y. And controlling for these would introduce a direct path between X and Y that is not there. And that is something that if you control for it, it will bias your estimates. So they automatically block backdoor paths. You don't need to control for them. But there are cases, as before with S, where you could have a variable that's a confounder on one path and a collider on another. And that was the main thing that was confusing for me when I was doing causal inference on big data sets. And then the final case here is mediating variables. So you'd have X calls Z and then Z calls Y. These orange arrows is the indirect effect of X and Y, but you might only care about the blue arrow X and Y. So mediators, they introduce this indirect effect of X and Y, and if you only care about the total effect of X and Y, then you don't need to control for M. And they're like another kind of way of spicing up causal models. So in summary, causal questions are ubiquitous. We've seen an example from today in the news where there is this kind of confusion around association versus causality. And causal effects can be estimated without randomized experiments, fortunately for us. It's something that's taken, well, it's only the last 20 years or so where we've had that kind of knowledge in stats community kind of outlined to everyone. The causal diagram is useful for modeling. You can iterate with it. You can involve other people in the business to map out other variables that affect what you're trying to estimate. In types of biases, control for confounders and beware of colliders. That's something that troubled me with econometrics, with these things called bad variables, bad controls. And then there's tooling out there now that can help you to choose your control variables for scaling out to large data sets. And if you want to look at further resources, Judea Pearl's Book of Why is a great one. It was quite a read for me when I was first picking it up because I came in with knowledge of econometrics and that confused things for me a bit. And then if you want an introduction to applied econometrics, Angaris Pishka, Mastering Metrics. Pishka was my professor at the LSE and he was great at explaining things in a basic way. So if you have stats and maths knowledge at university level, then it's something that could be a good read for you. And then Python libraries, if you want to do linear models, stats models the main one, linear models is another good one for econometrics, and then my package ApplePy can help out with encoding variables, diagnostics. It's like a fun thing for me. And yeah, this is my GitHub handle. That's it.
Yeah, thank you for the talk. I had one more question, I guess.
Sure.
Yeah, to how many variables do you think this kind of approach is scalable? Is it like hundreds, or is there an upper limit?
To my knowledge, there's not really an upper limit. If you look at other companies like Uber, so say for Uber Eats or Airbnb, they often have causal inference teams that you harness all their big data, hundreds of variables from different products and things like that, and they have these things called causal engines where they can pipe in all these different things, and yeah, so like, look at that DAG and then think, okay, well, running this on whatever scale, these are the things to control for. They had that figured out. So yeah, to my knowledge, there isn't like an upper limit to this.
Okay, one last question, perhaps? No? Oh, yeah.
Hi, I'm wondering if you go with a more traditional approach, in your example, like of identifying the importance of the features in messages and Google source, how different of a result would you get? Would you go the exact opposite direction, that something is important and has a positive effect, where it has a negative one? Are there cases where you're going to get the same insight and cases where you're going to get a different one?
So you're talking about things like model specification. So if you change an arrow in a different direction, say.
I'm mostly wondering if you don't go with causal inference. You do traditional, you fit a model and then you go with feature importance as a means to get an insight for, for marketing or an executive team. Are there cases where you would get a different insight, or are you going to get, a similar but incorrect type of number estimate about the effect?
Yeah, so by feature importance, I think you're talking more about machine learning algorithms. So if you did linear regression in sklearn or random forest and you saw that, what would would there be differences compared to doing it in the causal way? So in summary, I think that you could have different effects if you just threw everything in the model, all the variables, and then feature importance. It might, if two variables are strongly correlated, but one of them you shouldn't control for by the causal diagram, it would then have the impact of making your estimates more biased. There's less precision because you start to get more collinearity in the model, and that can increase your standard errors, that kind of thing, if you're doing a kind of basic linear model. So yeah, feature importance, it's calculated a bit more differently in machine learning compared to what you do with p-values on, or in an f-test on basic linear models. So I mean, there would be some similarity you'd expect, doing linear regression in sklearn and doing it in stats models, but yeah, it's all kind of dependent really on what you include in your model.
Okay, thank you very much, Mark. Let's thank the speaker again, please.